Hey learners, welcome back to ByteClassroom, where we teach tech one byte at a time. Today we are going to discuss about how programming works. We will see some exploration from machine code to the full stack programs. So far we have explored why should learn programming and how to think like a programmer. Now, in this video, let's answer a deeper question many beginners skip. How did programming actually start? What's the difference between a compiler and an interpreter? What's front end, back end, and full stack? If you ever jumped straight into Python programming, Java programming, or any other programming language without understanding how programming evolved, this video is for you. Let's take a journey from zeros and ones to full stack development. Let's rewind to the early days of computing, how programming started. Imagine it's the early days of computer. No fancy screens, no apps, just a big machines. And the only way to talk to them is through zeros and ones. That's machine learning, the language of the hardware. It's like using a Morse code to talk, but instead of dots and dashes, you have only the zeros and ones. Everything from math to messages had to be broken down into these two signals. Tedious, right? Writing instruction using just zeros and ones was slow, tedious, but it's error prone. So, machine language is the lowest level programming language made up entirely of binary code, that's zeros and ones, which is directly executed by a computer's CPU. It's not human readable, and each binary instruction corresponds to a very specific operation like adding the numbers, jumping to a memory address, etc. Machine language is the native language of the CPU, offering maximum performance but zero readability. That's why we use higher level languages and rely on assemblers, compilers, and interpreters to bridge the gap. Let's see an example like when we write an x86, one second, sorry, okay, instruction to move the value 97 into the AL register. Remember, x86 original referred to a family of Intel processors. I will write one sequence with zeros and ones. 1011 and then 0000 01100. This is how machine code will looks like. Weird, right? We don't understand what it means. The same can be written in assembly language as move AL 97. So what it represents? This the first sequence 1001011 and four zeros. This represents or this is an opcode for this move AL. Opcode which means operation code, okay? Operation code. It's a part of a machine language instruction that tells the processor what to do. So here, move AL97, which means take the number 97 and store it in the AL register. And this one 011 00001, what it represents is like a binary representation for the decimal number 97. So what is decimal number? Decimal is our everyday number system, also known as a base 10. Okay, so it uses 10 digits from 0 1 2 3 4 5 6 7 8 and 9. Each digit's position represents power of 10. Suppose, consider a number. So 472. This can also be written as 4 into 100 plus 7 into 10 plus 2 into 1, which means 4 into 10 square plus 7 into 10 to the power of 1 plus 2 into 10 to the power of 0. So this is how we will be representing the decimal numbers in general on the scale of a base 10 or power 10. Okay, so you may have a question in mind. Why does this matter in computing? It's simple. Computers don't use the decimal internally. They use binary, which means a base 2, or hexadecimal, which is a base 16. But we humans often input and read the values in decimal for our easy understanding. Now you all know why we are go for a assembly and a high level programming language instead of using a zeros and ones. I hope it's clear. Did you know the first ever programmer was not around when computers even looked like today? The fun fact in the above content as mentioned is the first programmer ever is Ada Lovelace. Back in 1800, wrote an algorithm for a machine that did not even exist yet. Can you guess what it was? Drop your guesses in the comments. You might be surprised when you hear the answer. And the next moment is like binary code, that is a zeros and ones can represent not just numbers but letters and even images. So what do you think the word hello looks like in binary? Take a shot and post it below. Now we are entering into a second level, that is assembly language. People thought there has to be a better way. So we got assembly language, a slightly smarter way to code. Assembly language is a low level programming language that uses mnemonic codes, which means human readable instruction to represent machine level instruction that we have seen right in binary zeros and ones. It acts like a translator friendly version of a machine code, easier for humans to read and write when compared to the machine level language, but still very close to what the CPU understands. Instead of a binary, we wrote short codes like you will often see instructions like MOV, which means move data, ADD, addition process, and SUB, subtraction, and JMP, jump to another location. Especially if you are diving into embedded systems, OS development, and scenarios like this. And some statements like move AX 10. So what it means is like load 10 value into the AX memory and move BX20, which means load 20 into the BX. And now if I give add AX comma BX, what it do is like additioning a BX to X. So at the last, the 30 10 plus 20, right? So this 30 value will get stored in the AX. But we'll still needed to way convert these codes into a machine code because a machine can't understand these words directly. Here comes a translator like we need when we don't know the language to communicate or process it. That's where the assembler came in. Assembly language bridges the gap between human logic and machine execution. It gives you direct control over hardware with less complexity than raw binary, but more complexity than the high level languages. And this sample assembly language code will be like this. Here we are doing some simple process like adding the two numbers, declaring three integers a and b are initialized and c will hold the result. That a is here. in this code is an inline assembly embedded within the C code. It allows direct use of CPU register level operations. Load value of A into the register AX, load value of B into the register BX, and adding AX, BX to AX. That is AX equal to AX plus BX. Store the result from AX into the variable C. Last inline prints the value stored in C, which is the sum of A and B. You may ask the question or having some kind of questions like why you use assembly inside the C. In simple terms, if I need to explain means it has three main reasons. The first reason is like for low level optimization. Secondly, to directly control the CPU registers. And lastly, often used in embedded system, device drivers, or performance critical code. So because of this only, we will be use assembly inside the programming languages. So fast forward a bit, it's time for the high level languages. Now let's fast forward. Humans wanted to write a code in normal English like syntax. That's how high level languages like C, Java, Python, and many more languages came in. A high level language is a programming language that is close to human language and abstracts away hardware details. It's designed to be easy to read, write, and maintain. You focus on what you want the program to do, not how the CPU should do it. So that comes a difference, right? High level languages let you focus on logic, creativity, and solving real world problems without worrying about internal workings of a hardware. For example, instead of saying move ax comma 1, we now write it as x equal to 1. Simple, right? It's easy to understand in a better way. But here is the thing. Computers still only understand zeros and ones, not x equal to 1. Okay. Now we will understand the difference between machine level assembly and high level programming in a nutshell. In a machine level language, the instructions are in a binary, that is zeros and ones. And assembly, we have a mnemonic code like we have seen, right? MOV, add, and SUB. And in the high level language, we have English like syntax like print, input, if else, like that. So this is how the difference will be like. It's represented in the binary series like a zeros and ones, and mnemonic code and English like a syntax like a x equal to 5. Now I hope why we are running behind the high level for most of the real time scenario when compared to the machine level language and assembly. Still, assembly language has its own importance and unique features also. But on the whole, high level programming language are the thing we'll be using for many of the IT firms and different sectors. Okay. So we need some tools to translate our code. So these are the not two, three main translators we'll be using if I'm using any programming languages. One with respect to compiler and interpreter, assembler. Let's decode these three translation tools. A compiler. A compiler works like a translator that converts an entire program written in a high-level programming languages like C, C++, or Java into a machine code that is zeros and ones that computer can understand. Analogical understand if I'm saying what is a compiler is like cooking the entire meal and then serving it at once. So the next question is how the compiler works. As we know, if it works in a high-level programming language, let's take an example: C programming language. A simple statement, okay? Int x equal to 5 plus 3. This is a simple statement in C. For this, uh, the very first step is like a lexical analysis. So it's almost like a tokenization. So what it means is like tokenization or lexical analysis is the source code is broken into tokens. So what is token here? Keywords, symbols, identifiers, and then it removes a white space and comments. So the above code is broken into tokens as like int, this is a keyword, right? And x is an identifier, or we can say in specifically variable name, and equal to what it means, assignment operator, and 5 is a constant, 3 is a constant, and plus is a arithmetic operator, and this a colon, which means a statement terminator. So like this it will get separated. And the second step is like syntax analysis, or else we can say it as a parsing. So what it does is like a check if the sentence follows the grammar of C, like we are checking with respect to a English normal statement. Is this a valid variable declaration and initialization? Yes. So it builds a parse tree like something like equal to. So this side we have x and this side we have a plus what we are adding 5 and 3. So it's almost like a grammarly. So it checks the line each and every statement like so like that it will do. This is the second step, syntax analysis. And the third step with respect to this thing is like a semantic analysis. So checks for the meaning are variables declared before use or types compatible, ensures logical correctness. Confirms X is declared before it's used. Checks that 5 plus 3 results in a valid integer, that is int, and confirms that assigning an int to X is allowed. So all good here. So this is how it checks the semantic analysis. And the fourth step here is like intermediate code generation. The compiler creates a middle layer code. It's almost, we can say, like a platform independent. Example, Java uses bytecode, and C or C++ programming language may use three address code. So we have this intermediate code generation. Mostly we'll be going for this two, right? Either the bytecode or the three address code. So for C programming language, we use a three address code. So what it means is like it assigns a T1 equal to plus 5 plus 3. So X equal to T1. This is easier for the compiler to work with and optimize. And the next step is like a optimization. So here it improves the performance of the code. Example, removes a redundant calculation, doesn't change the output, just make it faster or smaller. Like since the 5 plus 3 is a constant expression, the compiler can simplify it as a x equal to 8. That's it. Instead of a 5 plus 3. This reduces the runtime work, right? So this is what the optimization will do. And the next step is like a code generation. So in this step, it converts the intermediate code to the machine code for the target CPU, and store the output file is like what .exe or .out, depend upon the OS that we are using and the processor that we are using. Suppose if you are using an assembly for x86, might look like move ax comma 8 and move x. The term excite, like as I said right here, the refers to a family of instruction set architectures. used by many Intel and AMD CPUs, because most of our CPUs are either we have Intel series or AMDs, right? When we say x86 instruction, we are talking about instruction written for the processor that follow the x86 architectures, like uh, uh, Intel 8086, or like we have some series like 80286, 386, or 486, or even the Pentium series, and even some modern CPUs, they have versions like x86 and 64 versions. So an x86 instruction is a command in a binary machine code or assembly that CPU understand and executes according to the x86 ISA rules. So ISA in the sense, like as I mentioned earlier, instruction set architectures. Okay, and last step in the compiler is like linking. So in this step, it links this compiled code with libraries like stdio.h if user elsewhere, and outputs a final executable file like a.exe or main.out, depends upon the OS that we are using. So this is how the compiler works for every programming languages, like in a high level programming like C, C++, and Java. Okay, I hope you understand how the compiler works. And next we'll move to the interpreter. So, an interpreter is a program that executes code line by line, translating and running it on the fly without converting the whole program to machine code at once. Example is Python and JavaScript. So, the analogical understanding is like a chef who cooks and serves one dish at a time. So usually it happens in every hotel, right? We will order a list of items, but after everything get processed, then only we'll be able to get, not as a whole. So we see how this interpreter works actually. Let's take a Python example. The same in a Python statement x equal to 5 plus 3 and print x. Here also the first step will be like a lexical analysis, as we have seen with respect to the compiler. Just like a compiler, it breaks the code into tokens. Like here we have x equal to 5 plus 3, 5 plus 3 and print bracket x comma, I mean like a bracket. So this is how it will separated all those statements into a tokens. And the second step will be like a parsing. So it builds an abstract syntax tree to understand the structure. For example, so as I meant, like left side we have x, right side we have 5 plus 3. And the third step will be like a interpret and execute line by line. So what it uses, like it executes the first like statement x equal to 5 plus 3. So it evaluates what is 5 plus 3, we have 8, and stores this 8 value in x, as simple. And the second statement we have is like print hex. Fetch, what it does is like fetches the value of x, what it's 8, and send 8 to the output console. So that's how the 8 gets printed in the console. Now, what's a real difference between translating line by line versus like translating all at once? Think of its way. Like an interpreter acts like a narrator reading a story one sentence at a time, pausing after each line to explain. A compiler, on the other hand, reads the entire book first, then gives you the full summary in one go. It again depends upon the programmers like us or users like us to use. Either we can opt for the interpreter or for the compiler. So with an interpreter, the code run at its being read. With a compiler, the whole code is translated first and then programmer runs from start to finish. So why you use an interpreter? Great for learning and testing. That's like immediate feedback. Easier for dynamic typing and scripting, and useful for rapid prototype. You might be wondering, wait, where do this Java programming language and Python programming language fit in, right? So Java actually works both compiled and interpreted. First, the Java code is compiled into something called bytecode using Java C, and then with the help of a Java virtual machine, that in simple we call it as a JVM, right? Interprets the byte code line by line when you run the particular program. Think of it like preparing a full recipe but serving it byte by byte. Python, on the other hand, is primarily interpreter. So when you write a Python script, the interpreter reads and executes it line by line. There is no separate compilation step like Java. It's a direct and dynamic. So in short, Java, which is having both a compiled and interpreted, and Python is an interpreter. This is one reason why Python is a beginner friendly, quick to test, run, and even to debug it. Okay, I'm not supporting the Python programming language. As we have going to see the Python programming language, I'm comparing to another competitor like Python, sorry, Java. Okay, now the last translator called assembler. An assembler converts assembly language like human readable mnemonics into a machine code, which means like a binary instruction that the CPU understands what? Zeros and ones. So we'll take assembly a simple statement to see how assembler helps in conversion. Okay, and here we are seeing a move AX5 add AX comma 3. So as the first and the foremost step is like a lexical analysis. It breaks down each line into tokens like move, AX, and 5. And second, A add, AX, 3. And the second step is like a opcode translation. Each mnemonics like this move and add code represents to a specific binary code. So here, uh, like move AX comma 5, this become like this. I think I'm right, I guess. So each value has something, and this one is 5 and represented. I mean, like a binary version of 5, and this is opcode for this one. Same with respect to the second line. Add AX3, and here AX is represented by this sequence of zeros and ones opcode, and the 3 we all know it, right? I'm a 0. Fine. Hope I get clear. Okay, these are defined by the CPU's instruction set like x86 or ARM processor. And the next step will be like a symbol resolution if it presents in this particular thing. If the program has labels, variables, or jumps, the assembler assigns memory addresses like move AX0 JMP start. It needs to know what address start refers. This is called the symbol resolution. Okay, so in the assembly programming language, we all will be doing like this only, and generate the machine code. That will be your next step. Machine code. The assembler writes the binary equivalents of all the instruction and data into an object file, either like a obj or .o. Again, depends upon the OS and the processor that we are using. In machine code, for say for example, 16-bit x86, that this becomes something like what B8, 05 and 00. This B8 is a opcode for move AX and the 05 number 5. Okay, like a little Indian form, and same as uh, 05, 03 and 00 for the code, assembly code, add AX3. And the 05 is the opcode for add AX, and 03 and 00 is the number represented for the number actually 3. Okay, again the little Indian format. And last option, it's optional, it's not a compulsory thing, like linking. If multiple or libraries that we have used in the code, a linker combines them into an executable format. Okay, so then only we'll be able to get a single output for every program, right? I hope I mean, even though it's like a bit confusing, we are not going to see anything deeper with respect to this assembly language, but we need to understand, right, like how this assembly language works. We can write a single statement, but behind every statement there is a large process. So that also we need to understand, right? Fine. Now we are move on to the domain specific and AI focused languages. As the tech world evolved, so did the programming languages. Imagine a cafe where each table is reserved for a certain kind of a genius. You walk in and see four different tables, each with a unique focus. Let's take a look. The table one is the AI thinkers. At this table sit the brilliant minds of AI and machine learning. And here, for this particular thing, we use Python, R, and Julia. Why Python is a superstar here, right? Friendly, flexible, and with a toolbox full of libraries like TensorFlow, PyTorch, Scikit-learn. We do some kind of a blenders. And R is sipping data charts, like perfect for statistical modeling and data visualization. And Julia is a speedster, is a rising in fame, combining Python's ease with the C-level speed for heavy mathematical workloads. Because AI needs fast prototyping and data handling and community-backed libraries, these languages they deliver in style. And second stable is like web architects. Moving to the front end of the digital world, here are the web builders. JavaScript is a lifeline for the web, controlling interactivity, behavior, and responsiveness in browsers. And second most important language is like a TypeScript. JavaScript's smarter sibling adds strong typing for few bugs and better team collaboration. Because the web runs on browsers and browsers run the JavaScript, TypeScript builds on that with the developer friendly features and scalability. Then in table 3, the data crunches. Over here, you will find some data wizards like SQL is a language of databases, retrieving, filtering, and managing structured data with laser precision. And MATLAB is a go-to for numerical computing, specifically in engineering and scientific research, because they are designed to manipulate and analyze large data sets with the built-in tools tailored for data operations. And lastly, in table 4, the game masters. And finally, the table with controllers and graphics, the game developers. Uh, C Sharp and Lua, GD script. These are the languages will be exclusively used for this kind of programming, sorry, game development. So here the each language is like a tool, and the best tool depend on the job, whether it's teaching a machine to think or designing a web or crunching numbers or building immersive worlds. The right language can turn code into the magic. Each one is designed with a purpose in mind, just like you use different tools for cooking, cleaning, or painting. And we often see these jargons when it comes to job profile, front end, back end, and full stack. Let's connect these dots with another modern concept like front end. What the user sees, buttons, menus, colors, and these are built with the HTML, CSS, and JavaScript. It's like the outer design of your mobile phone. And the second is like a backend, how things work behind the scenes, servers, databases, and logic. So for this, we'll be using languages like Python, Java, PHP, Node.js, etc. And example, the internal circuit board inside the phone. And the full stack, a developer who does both, they can handle the front end plus back end, the full picture. So for them only, we call it as a full stack. So, why this matters? Now you might ask, why should I know all this before learning Python programming language or any other programming language? Because knowing how programming evolved, how code gets translated, what the layers of developments are, helps you become a better and more confident programmer. You won't just write code, you will understand what's happening under the hood. Even if you aim to become a data scientist, a Python developer, or a full stack developer, understanding these foundations shows you how or what to prepare and why giving your learning a stronger direction. It gives you a clear roadmap, not just for writing the programs, but for solving a real world problem efficiently. So, Uh, let's recap a bit. We have started at zeros and ones, that machine language, moved to assembly, a slightly easier version when compared to the machine language, then to high level languages like Python and Java. We explored how they translated using compilers, interpreters, and assemblers with some basic simple statements. Even we discovered how different domains choose different languages for their needs, and wrapping up with front end, back end, and full stack rules all fit together. This foundational knowledge helps you code with confidence because you will understand not just how but the why behind everything you write. Finally, from this video, one thing we can conclude is if you don't know the roots, you won't understand the branches. So it's not about only coding alone. We also need to understand the basics before coding. Remember, I asked two fun questions during the video, right? Don't forget to drop your answers in the comment. So in the next video, what we are gonna see is like, I hope you people won't forget the topic, the what's the difference between programming and coding that we have seen in the previous video, right? So coding is not only the solution to any problem statement. Before we write code, we need to understand the logic, and before logic, we need some clarity. That's why in the next video, we won't jump into Python programming language. We will first learn how to approach a solution for any kind of a problem statement before we code. Through PAC, algorithms, flowcharts, and pseudocode, we need to think it, draw it, and then at last we code it. Hit like, share with your friends, and subscribe. I end the video by punchline. Don't just be a coder, be a creator who understands why behind every line. Until then, this is Premanam from ByteClassroom, where we teach tech one byte at a time. Stay curious, stay logical, happy coding.